So in this video, we're going to talk about levers. And levers are a type of simple machine that are made of two main components. The first is a rigid beam, and the second is the fulcrum, which is also often referred to as the pivot. And levers allow a force that's applied at one point, which we call the effort, to move a load that's placed at another point. So for example, in this illustration, we see if the effort is large enough to overcome the resistance of the load, well then the beam will translate down on the left, it will move up on the right, and it will do so about the pivot point, or the fulcrum. So let's cover two more fundamental concepts when you're talking about any lever, and that's the effort arm and the load arm. So, for example, the effort arm is going to be the distance from the position where effort is applied and the fulcrum. And likewise, the load arm refers to the distance between the load and the fulcrum. Now, why do these two values matter? Well, of course we know that the size of the effort and the load play a role in lifting the load or balancing the lever, but their position relative to the other components is also critical. So we can use the effort arm and the load arm to understand and predict how a lever will behave, and more importantly, the mechanical advantage. So mechanical advantage is basically the entire reason why people use simple machines like a lever, because mechanical advantage makes it easier to lift a load. Or in other words, it requires less effort with mechanical advantage. And for a lever, the mechanical advantage is simply equal to the effort arm divided by the load arm. And when a lever has a greater mechanical advantage, it's because the distance from the effort to the fulcrum is longer than the distance from the load to the fulcrum. So for example, referring to our same illustration, the position of the effort and the fulcrum, that distance is equal to the distance between the load and the fulcrum. So in this case, the effort arm and the load arm are equal, and the mechanical advantage would have a value of 1. So let's take a look at a practical example of mechanical advantage in levers, and essentially how this all works out in practice. So remember, levers provide mechanical advantage. That's why we're interested in levers. And it's because it makes it easier to lift the load. It requires less effort. So let's look at a similar system to the one we've been working with thus far with a few important changes. So first of all, we're going to use a second load to represent the effort. So here on the left, where we have this square labeled 1, this is going to represent our effort. And on the right, we have our load. And we can see the load has a value twice that than the effort. Conversely, the effort arm, so the distance from where effort is applied to the fulcrum, is twice as large as the load arm, or the distance from the load to the fulcrum. So what do you think is going to happen? Do you think this should be balanced? Do you think that the load should be lifted? What do you think? Well, again, we have a load with twice the value as the effort. But because the effort arm is twice that of the load arm, this compensates for the different magnitude between the load and the effort. And in this case, this would be balanced, even though the mechanical advantage is relatively large for this. Remember, the mechanical advantage for a lever is equal to the effort arm divided by the load arm. So if the effort arm is 2 and the load arm is 1, that means the value for mechanical advantage would be 2. But because the load is twice that of the effort, this essentially cancels out, and we would expect the situation to be balanced. Now, what would happen if we moved the fulcrum to the left? Well, if we move it to the left, that means the effort arm becomes shorter. It will become less than 2. But the size of the load and the effort don't change, but the mechanical advantage went down. So in this case, we would expect to see the load the load side of the beam start translating down, and the mechanical advantage would go down. Now, the opposite is also true. If we were to move the fulcrum to the right, well then in this case the load arm is getting bigger, which means the mechanical advantage is getting smaller. And in that case, we would see the opposite effect. We would see the left-hand side, where the effort is being applied, go down, and we would see the right-hand side with the load go up. So up until now, the lever we've been using as a reference is actually a specific type of lever, and it's called a Class 1 lever. And in a Class 1 lever, the fulcrum is located directly between the effort and the load. So up until now, we haven't really considered the arrangement of the fulcrum, effort, and load with respect to one another. But actually, this is a very important part about what levers are and how they work, and their relative arrangement define the type of lever. So again, in a Class 1 lever, like a pair of scissors, for example, the fulcrum lies in between the load and the effort. So for scissors, you're of course applying the effort at the handles. You have the fulcrum or the pivot in the middle here at the pin, and then the load here sits between the blades. And some other common examples of a Class 1 lever include seesaws, scissors, as we've seen here, and pliers. So now moving on to a new type of lever that we haven't discussed, we have the Class 2 lever. And in a Class 2 lever, instead of the fulcrum being between the load and the effort, it is the load that is placed between the fulcrum and the effort. And a common example of a Class 2 lever is a wheelbarrow. And again, defined as a Class 2 lever, this means that the load will be in between the fulcrum and the effort. And in a wheelbarrow, you're applying the effort to the handles. The load sits within the basket of the barrel in the middle of the system, and then the fulcrum or the pivot is the wheel. So as you apply effort to lift the handles and lift the load, it will pivot about this wheel. And some other common examples of a Class 2 lever are bottle openers, nail clippers, and staplers. And lastly, we have the final type of lever, which as you can expect is called a Class 3 lever. And in a Class 3 lever, it's the effort that's positioned between the fulcrum and the load. So each class of lever basically puts a different element in the middle of the other two. And a common real-life example of a Class 3 lever is a fishing rod. So again, Class 3 lever means the effort is in the middle. Let's start by identifying the effort. Well, the effort is applied by the fisherman's right hand towards the top, which is pulling the load. And on the sides of the effort, we have the fulcrum. So this is essentially the fisherman's other hand. This is where it will pivot. And then, of course, we have the load, which is really the fish at the end of the line. So again, Class 3 lever, effort is in the middle of the fulcrum and the load. And some other common examples outside that of a fishing rod is tweezers, baseball bats, and ice tongs. Summarize what's important here. Levers are simple machines that are made of two main components, a rigid beam and a fulcrum. They're used to make it easier to lift load by providing mechanical advantage. Remember, when we're talking about simple machines, it always comes back to mechanical advantage. And mechanical advantage makes it easier to move a load. And for levers, the mechanical advantage is equal to the effort arm divided by the load arm. And in general, there are three types of levers, a Class 1, Class 2, and Class 3 lever. We have a Class 1 lever where the fulcrum is located between the effort and the load. We have a Class 2 lever where the load is positioned between the fulcrum and the effort. And lastly, we have a Class 3 lever where the effort is positioned between the fulcrum and the load.